Welcome to my channel Maithili SK. In this session, we are going to see about our next topic, spectral characteristics of angle modulated signals of Unit 1 communication systems. So in this session, I am going to cover you with the introduction to the spectral characteristics of an angle modulated signal. So I will be explaining what is actually spectral characteristics and the important concept of a point which is to be noted in angle modulation is the Bessel function. And next is the significant sideband and the plotting of an FM signal. Then importance of spectral characteristics and application of spectral characteristics. So coming to the introduction part of a spectral analysis of the signal, we'll see what is spectra first. A signal under study of a communication system is generally expressed as a function of time or as a function of frequency. So either it will be in a function of time or in a frequency. So when the signal is expressed as a function of time, it gives us an idea how instantaneous amplitude of the signal is varying with respect to the time. So here the signal component is represented in terms of scale axis. Please do you remember or recall? So a signal which is represented in terms of, let us consider a sinusoidal signal. This is time scale and this is your amplitude scale, the signal representation. So here when the signal is expressed as a function of time, it gives us how the signal is varied instantaneously with respect to this time. So this is the time scale. Whereas when the same signal is expressed as a function of frequency, it gives us an insight of what are the contribution of different frequencies that compose up that particular signal. That is, what is contained with that signal will be represented in terms of frequency scale. So example, if Bessel's function is represented, we'll be seeing the Bessel's function component here. So if this is the signal representation, if it is taken in terms of frequency component with respect to FM and minus FM, instead of T, we will say the maximum signal will be contained within the bell-shaped curve of the signal, not with the least part. So here this is the signal component which contains the maximum signal. Example, if I am speaking, hello, how are you? This is the message. So this message will be contained maximally within the bell-shaped curve of the signal. So this frequency analysis is very important when we are representing the signals. So this is the analogy part and this is about the spectral part. So basically a signal can be expressed both in time domain as well as in frequency domain. So this is for your analysis. So in order to understand the frequency component terms, so we are talking about the frequency component, how a signal is contained in the spectrum, right? So if I am talking about the signal contained in the spectrum, we want to study about the signal. So how this can be done is nothing but we'll be using various mathematical tools to get the frequency domain expression of this particular signal. So that signal, that study involves our mathematical tools or nothing but your Fourier series, Fourier transformation, etc. So we have studied x of t signal, how it is converted into x of f in terms of transformations, right? So this Fourier series and Fourier transformation helps us lot in analyzing this signal component which is represented in continuous domain with respect to frequency domain component. So spectral characteristics of a signal. Actually, here comes the definition or real part technically. Spectral characteristics of a signal refers to a distribution of the signal's power. Refers to the signal's power. Let me take the spectral characteristics of the signal refers to the distribution of the signal power across different frequencies, essentially describing the frequency content of the signal, including details like dominant frequencies, that is highest frequencies, its bandwidth and overall shape of its spectrum, which can be analyzed using different techniques like Fourier transform to reveal the important information about signals' nature and origin. So as we have previously involved, just to relate with this signal. So if this is the signal representation, we'll be studying about the dominant frequency part because it contains a maximum signal. So that is studied here, and its bandwidth is studied here, and the shape of this signal is also studied here. How all these is studied is by means of using this and techniques called as Fourier series and Fourier transformation. So due to inherent nonlinearity of angle modulated systems, precise characterization of their spectral properties, even for simple message signals, is mathematically untraceable because the signals are unpredictable. Because we can say, if I'm speaking here, this voice signal, when it is represented in a spectrum, how it will be appearing, you might analyze or you might recall. So my message signal or voice signal will be like this only. So you can't take the component or frequency component of each of the signal. So how you can relate this signal is nothing but you just compare the signal when some voice is being traced. It is shown in various movies. So voice messages, if you talk, how the voice message is jottering between high frequency and low frequency components, you could see when it is when our voice is very streak and high, it will be very having a high spike, whereas when it is low, it goes for low spike. So just to record your voice and see this in this signal representation is shown in your mobile apps itself. So that is how the what is what the spectral properties is. So this, due to this characteristics, what is we have obtained here is this, mathematically we can't predict the equation for this kind of signals. So derivation of spectral characteristics of these signals involves a study of simple modulating signals and certain approximations. So we'll be involving with simple modulating signals, and approximations is to be done to study what kind of signal is being transmitted. Then the results are generalized to more complicated messages. So here we will be studying the spectral properties or characteristics of an angle modulated signal when the modulating signal is a sinusoidal waveform. So now considering an angle modulation signal which is having a sinusoidal characteristics. So we'll be considering two signals for FM and PM. A message signal is considered. So S of t is a signal for considering a message signal case for FM or AM. So this beta represents your modulation index. So when it is represented as BF, it is a frequency modulation index, and when it is represented in P, it represents a PM's modulation index. So AC cos of omega CT plus beta into sine omega MT is a message signal. So as I said, this is the modulation index. So the modulated signal can be written as in terms of real component and complex component here. So S of t is nothing but real component of AC e power 2 pi omega ct into e power j beta into sine of 2 pi fmt. So sine 2 pi fmt is nothing but a periodic representation of the signal with the periodic of omega. That is, here this is your omega term. So here considering in terms of t, it becomes 1 by fm. This is also equivalent or true for a complex exponential signal. So it can be represented as e power j beta sine 2 pi fmt. So therefore, it can be represented or expanded in Fourier series representation format. So the Fourier series coefficient terms of this CET signals is taken as Cn equal to Fm, ranging for a value of 0 to 1 by Fm over the period. So e power j beta sine of 2 pi Fm omega t into e power minus jn 2 pi Fmt into dt. So we are considering this with respect to u equivalent to 2 pi fmt, means it becomes 1 by 2 pi for a ranging a period of 0 to 2 pi e power j into beta into sine of u minus n into u into du. So we are substituting here instead of this term as u and representing or arriving at a common solution. So this later integral is a well-known integral. So if you integrate this term of equation number 4, we'll be getting the Bessel's function of the first order. of nth order. So there will be n orders which is taking place because it is infinite in series, we can say. So we have arrived at a function known as Bessel function, and this equation will be represented as a first component. This is as we know, the component when it is oscillating will be having a fundamental frequency, then it goes with the first order, second order till nth order. So this is your first kind of the order of n, denoted by Jn of beta. So therefore we have the Fourier series of for a complex exponential term. So e power j 2 pi fmt is nothing but summation ranging from minus infinity to plus infinity in Jn of beta term e power j 2 pi n into fmt. So this is your Bessel's function component. Now substituting this 5 in second equation, we will be getting function of u of t with respect to real component. Instead of that, we are going to substitute this term of e power j 2 pi fmt. We are going to substitute the whole term of the Jn Bessel's function. So we'll see here AC will be representing AC into summation part Jn beta e power j 2 pi fnt into e power j 2 pi omega ct, that is a 2 pi fct. So arriving at these two functionalities and rearranging the same, we will be getting AC Jn of beta into cos of f 2 pi, the taken outside, fc plus n into fm of t. So equation 7 is showing a equation that is it represents even in this simple case, that is we are considering with respect to Jn expansion term. With respect to this, this is a sinusoidal. This representation, which is in an exponential format, is again converted in terms of cosine functionalities, which shows a simple case where the modulating signal is a sinusoidal of the frequency component fm, the angle modulated signal, which is containing the frequency range of all the terms ranging from fc plus n into fm. So here n can be ranging from 0 to infinity terms. So 0 plus or minus, so it has both plus value as well as minus value. So it is plus or minus n into fm. Therefore the actual bandwidth of the modulating signal will be infinite because it goes on extending. So that is the amplitude angle modulated signals. Sidebands are infinite number of sidebands. Now coming to the Archie's Bessel functions. However, the amplitude of the sinusoidal components of the frequencies fc plus or minus nfm for large n is very small. When we increase the value of n, the component will be very small. So we will be defining a finite effective bandwidth for this modulated signal. So based on the series of expansion Jn these terms, that is Jn of beta, we will be arriving and approximating the same equation in this format, and we will be arriving or giving it in terms of two terminologies, that is with respect to what happens when it is even case, what happens when it is one case. So for even for a modulation index, so defining a different modulation index and arriving at this Bessel's function, we will be arriving at a table which has the values of the Bessel function with respect to the number of n's. So here you could see here the number of n's is represented here. For increasing number of n's, you could see here the Bessel's function beta value is not present, so it gets decreased actually. So for the value of n, which is it is maximum for these number of values, and here the beta value which is ranging up to 10, we have only one value for n is equal to 16. So if it is a goes on increasing functionality also, this is the standard Bessel's function table, which is found by Zeimer and Tranter, and it is used for the Bessel's function calculation and the number of sidebands. So when they are asking about what are the sidebands and how it can be drawn for an FM signal, this table can be used very well. So this is the actual plot of the Bessel's function. You could see here. Actually, I drawn the signal with respect to only one component here. So it is nothing but the signal representation like this for a first term example. Then for the second term again it goes on like this, right? Then for the third term it goes on like this. So this is the way the signal is being represented. As I said, this is the maximum frequency dominant signal, that is the peak value of the signal which is present here. So the value here is 1. Between one value we could see here for various J naught of beta value how the Bessel's function plot is occurring. So this is the Bessel function of various values of n. So based on this you could represent how many sidebands are present. So if the table is given well off, you could draw the number of sidebands present for this FM signal. This is the table used here, as I mentioned. So the plotting of the signal can also be done based on the above table. So what are the terms used in a spectral characteristics is the power spectral, very important point is the power spectral density. It is a common way to represent a signal's spectral characteristics showing the signal power distribution across different frequencies. So this power spectral density is very important part when coming to spectral characteristics. Second part is nothing but the frequency components, which tells us which frequencies are present and their relative strengths. And third one is nothing but its bandwidth, the range of frequencies contained for each of the signal. And the spectral analysis techniques is nothing but which involves a Fourier or a Fourier series or a Fourier transformation, short time Fourier transformation, wavelet transformation, etc., which is used to get back the spectral characteristics from the signal itself. Next is the signal classification. So we have seen 4.1. This is the fifth one. This is the signal classification. So analyzing the spectral features of a signal. This can be helpful in identifying the types of signals which is relating to different sounds or it depends on different quality of a signal. So if it is an audio signal, how the signal is being represented is known. It is all analyzed based on these spectral characteristics. Then fault detection in machinery monitoring. This changes in the spectral characteristics can also identified by for using a fault detection technique. So we know the standard signal representation of a machine which is being running. This is also be analyzed here. So example, if you go and see a heart rate or there is a human heart rate as a standard signal, which is a spike signal, which has only 2 to 3 spikes. So if there is any variation, that signal is also analyzed to identify any fault detection. Example, heart failure, etc., ECG, EMG, all these are the applications we can say. Then about the signal processing, understanding this spectral content, allowing the designing filters which removes the unwanted signal frequencies is also an application of spectral characteristics. So what are the key takeaways of today's topic here is spectral characteristics deals with representation of signals both in time as well as in frequency domain. Sometimes it can be represented only in time or in frequency alone. And techniques used for spectral analysis includes Fourier series, Fourier transformations, and wavelet transformations. And for angle modulated signal, the message signal is represented in terms of exponential form. That is, we have represented in terms of e power j omega t. And for angle modulated signals, the signal is analyzed using this Fourier series and it is resulting a functionality which is known as a Bessel's function, and it can be given or it can be plotted based on the Bessel's function. That is, Bessel's function is nothing but equation what we have obtained for this analysis of the angle modulated signal, and for the same we can plot the function Bessel's function using various values of n and beta values. Hence angle modulated signals has an infinite number of sidebands because it ranges for plus or minus 1 to n. Important questions for today's topic will be what are spectral characteristics, just the definition, what is Bessel's function, and sometimes they can be asking about plotting of signal. This is very rare question, but if they are giving only the values, we can plot the signals of the same and state the applications of the spectral characteristics. So this is actually we have already seen with respect to AM signal. So for FM also we will be plotting the signal with respect to both the values. So here this will be your n equal to 1 plus or minus 1 and this is plus or minus 2, and this is your plus or minus 3. So for 0th value it is 0, etc. So here for both the sides you have to take the value. So if it is minus, for minus side it becomes plus, for plus side it becomes minus. That is the same. And in part B question, the possibility here is explain the spectral characteristics of angle modulated signals in general. Or sometimes they will be asking precisely explain in detail about Bessel's function. The same you have to write about spectral characteristics. Or derive Bessel's function is we have to derive Jn of beta term. That is also with respect to message signal representation, carrier signal representation, both in exponential form, then arriving at as Bessel's function form. Hope you understood today's topic. Our next topic will be Hilbert transform, pre-envelope and complex envelope AM techniques. Thanks for watching.